Hi, in this tutorial, we focus on simulating the electronic properties of materials, specifically strontium tantalate SRTA03. We began by setting up the working directory within the Ubuntu environment. First, the Ubuntu terminal was opened to create a dedicated project folder. The command copy and paste was executed to build the directory permission were updated and then was used to launch the window files interface for that specific path. Next, the necessary data parameter and cell file were downloaded. These files were pasted directly into the new folder. The template file was then renamed to SRTA03 cell to ensure the CASTEP solver recognized the correct compound. The SRTA03 cell file was opened and an external pressure block was added. A hydrostatic pressure of 0.003 GPa was applied across the diagonal of the stress tensor to stimulate the 3 atm environment. Once the values were entered, the file was saved. Configuring the param file. Afterward, the SRTA03 param file was modified. The task was set to geometry optimizations, which allowed the SRTA03 crystal structure to relax and reach equilibrium under the newly defined 3 atm pressure. All coverage criteria were double-checked for accuracy. With the directory prepared and the files correctly configured for 3 atm, the system was ready for the CASTEP calculation. This concludes the setup phase of the simulation. Running the calculation with the input files finalized, the simulation was initiated through the Ubuntu terminal. The common cast-step serial SRTA03 was entered to start the solver. For faster result, a parallel execution command like np-run np4 cast-step MPI SRTA03 was utilized, which distribute the workload across 4 CPU. Monitoring convergence. As the simulation progressed, the output was monitored in the real time by checking the SRTA03 cast-step file. This file provides updates on the self-consistent field cycle and the geometry optimization step. The software checked 4 key criteria: energy change, maximum force, maximum displacement, and maximum stress, to ensure the material reached a stable equilibrium at the 3 atm pressure was set. Editing cell angle and searching for space group. Check that all angles are exactly 90 degrees for the cubic system. Next, search the output for the space group. You will find it belongs to PM3M space group 221. In this cubic symmetry, the tantalum atom sits at the center of oxygen octahedra, which is key to the electronic properties we are about to calculate. Now, adding the BSK point path blocks. Now, we define the symmetry path through the Brillouin zone. For a cubic crystal, we use a standard path, gamma to M to X to R and back to gamma back. This allows us to see how the energy of the tantalum 5d and oxygen 2p electrons change as they move in different directions through the crystal lattice. Changing task to band structure in the param file. Next, open the param file. We change the task from geometry optimization to band structure. This tells cast-step to keep the atoms fixed in their optimized position and solve the Schrödinger equation for the electron energy level at the specific K point we just defined. Running the command in Ubuntu terminal. In the Ubuntu terminal, I execute the calculation using the cast-step MPI command for SRTA03. I wait for the process to complete, which took about 30 minutes, until the green compound names appear again, signaling a successful run. And then opening grace and viewing the band structure. Finally, I use the dispersion PL script to generate the plot. I specify the cubic symmetry and open the resulting bands file in grace window. I adjust the y-axis scale to focus on the area around the Fermi level. Once the plot was generated, I focus on the Fermi level represented by the horizontal dot line at 0 EV, I observed that several energy bands directly crossed this line, which confirmed that SRTAO3 was metallic under this condition. Because the valence and conduction bands overlapped, the calculated band gap was 0 EV, unlike SRTIO3, which is an insulator. The tantalum 3D electron in the structure remained mobile, providing the material with high electrical conductivity. I note that the gamma showed significant curvature or depression, especially around the gamma point. This high depression was a result of the large 5d orbital of tantalum overlapping with the oxygen 2p orbitals, suggesting low effective mass for the charged carrier. By analyzing the path from gamma to mx and r, I saw how the electronic states shift in energy across the Brillouin zone. The 3 atm pressure I applied slightly widened these bands compared to ambient pressure, further stabilizing the metallic state. In conclusion, the band structure successfully demonstrates that SRTAO0 is a metallic perovskite. The lack of band gap and the strong depression of the 5d bands were the defining features of this electronic profile.